Welcome to the computer design of electrical machines. We will have a lecture today on lecture 31 on design of synchronous motor part 1. Starting with the outline, with the introduction, application of synchronous machines, then construction and operating principle of synchronous machine, then modeling of SRM, exercise and numerical problems and references. Like coming to the introduction, the origin of this synchronous motor can be traced as 1842, but its reinvention it has been possible due to advent of inexpensive high power Polaris switching devices. So since 1969, a variable reluctance motor has been proposed for variable speed application, and switch reluctance motors are WC and singly excited electrical motors with passive windingless rotors, and these concentrated coil phases are turned on sequentially to produce torque through DC voltage pulses, which result in unipolar control current. So the power rating of switch reluctance motor ranging from 3 watt to the practically megawatt units, and it can work for low speed range, for low dynamics as well as high grade servo application, especially in thermally and chemically harsh environments. And type of machine is differentiated by number of poles on stator and rotor, and configuration available which are generally used are 6 pole on stator, 4 pole on rotor, then similarly for 8 pole on stator and 6 pole on rotor, then 10 pole on stator and 8 pole on rotor, and 12 pole on stator, 8 pole on rotor, and then similarly 12 pole on stator and 10 pole on stator, and many more configuration. Well, these are typical example like a two-phase. Normally we don't use two-phase because it does not have a bidirectional feature. We have to make a special arrangement, as you can see here. In the rotor we have to make a special arrangement with by varying the typically you can call it the air gap length in some portion of the rotor. But of course we make a three-phase motors with the 6 pole, as you can see here, with the 6 pole on stator and 4 pole on rotor. Then we have a large majority of configuration with four phase reluctance motor with 8 stator poles and 6 rotor poles, as you can see here. How typically even the winding excited, how it's get a langing. Like with the typically you can either have excitation of one phase or you can have excitation of two phase. Then of course you can see is a 4-phase 8x6 conventional rotor, and then we have a now 4-phase 8x6 segmented rotor switch reluctance motor, which are recently advocated. Like then 4-phase 8x10 conventional rotor switch reluctance motor and 5-phase 10x4 conventional rotor, that's a reluctance motor. Then 6-phase 12x10 conventional rotor reluctance motor. So these are the some popular configuration. Now we are coming to discuss the applications of this reluctance motor. People have developed the even the domestic fans with the switch reluctance motor, as you can see here, and then many kind pedestal fan, table fan, then exhaust fan, and then typically of course you can just see here the 224 watt 40 rpm to 10,500 rpm with the efficiency of 86% reluctance motor for blender, and you can see the characteristic how it really goes for typically with different torque characteristic. Then you can say reluctance pump motor drive, for both configurations, like as you can see cylinder pole structure on the stator and rotor, and how look like a assemble motor like. Then the textile machinery in repair looms and towel, etc. Then the oil refinery in vertical pumps being pumps, well testing machinery. Then the mechanical presses, then mining machinery include the shearing conveyor, winches, boring machine, ball mills and coal presses. Then food grinders, then typically 220 watt, 1000 watt, 13,000 SRM for mixer grinder. Then typically variable with controller. Then high torque reluctance motor, as you can see the geometry of stator and rotor here in open form. Even both the configuration are typically quite popular. Then the coin switch reluctance motor, a series of. Then of course these are used for electric vehicle. The feature of reluctance motor which are really very suitable for electric vehicle are high efficiency over a wide speed range of the operation, and very compact, cost effective, robust and reliable, and fault tolerant and sustainable. Then the typically you can see for SRM for motorbike of 250 watt 360 rpm gear DC. motor, then to replace that, and then 1200 watt Sri Lankan motor for e-rickshaw. Then you have 500 kilowatt Sri Lankan motor for electric vehicle. Then 60 volt by 72 volt high power Sri Lankan motor drive for electric car. And a motor generator for hybrid and electric vehicle with the gears. Of course, the motor normally designed at high speed, where the size of the motor goes low, and then of course with the gear we reduce the speed on the shaft to increase the torque of the electric vehicle. Then for electric vehicle, people have used the Land Rover Defender with the Sri Lankan motor. That the 2013 Journal Motor Show, Land Rover unveiled a range of new electric Defender vehicles which are directly powered by an electric motor and drive system developed and built up by Nidec SR Drive Limited. And Harrogate-based Nidec SR Drive Limited has pioneered and commercialized the Sri Lankan motor technology for more than 30 years and recognized as a world leader in the field. You can see the photograph of Land Rover Defender. So, in electric research vehicle, the standard diesel engine and gearbox of the Land Rover 110 Defender has been replaced by Sri Lankan motor drive of 72 kilowatt, 94 bhp Sri Lankan motor electric car, electric vehicle, and it was tuned with a 300 volt lithium ion battery with a capacity of 27 kilowatt hour, giving a range of more than 50 miles, and it has a top speed of 70 miles per hour, and in typical low speed off road can run up to 8 hours before recharging. The Sri Lankan motor technology developed by Nidec is exceptionally well suited to a Defender orders all-terrain traction needs, being able to develop full rated power over a wide speed range. And the Sri Lankan motor delivers 330 Newton meter of torque from stainless steel, and there is no need of gear shifting, and transmission complies with a single speed 2.7 by 1 reduction box combined with the existing Defender 4-wheel drive, as you can see in the photograph. Then this is another typically, let's say, controller motor of 2 kilowatt with a 4-quadrant high performance pilot truck drive for electric vehicle. So, another application is hybrid bus drive. So, in green propulsion series and parallel hybrid transmission system, a 50 kilowatt and 160 kilowatt SR drive motor generator both work in conjunction with 2.5 liter diesel engine, downsized from 7.5 liters in conventional bus. This combination is powered from lightweight, low loss lithium polymer battery and enable the vehicle to seamlessly switch between the pure electric running or hybrid power, whichever with you optimum efficiency. And this is a typical photograph of the hybrid bus drive. So, this technology also eliminates the need for a main gearbox, enabling direct coupling of the wheel drive, resulting in an improved efficiency at all operating speed. So, in test, green propulsion combined hybrid system achieved reduction in CO2 emission in excess of 40% and fuel saving over 30% compared to conventional diesel engine vehicles. Another key features of the green propulsion scheme is the use of low loss lithium polymer battery that provide significant weight saving and improved electrical efficiency compared with lead acid battery. So, this is typically internal photograph of the engine or motor, you can call it, of hybrid bus with different parts with the SI drive motor of 50 kilowatt with liquid cooling, and then of course another SI drive 130 kilowatt nominal 160 peak liquid cooling. So, this hybrid powertrain, the result is a design which meets all the performance requirement and has been demonstrated to be most cost effective solution when compared with the other electric drive technology, costing some 25% less than alternative system, and a 50 kilowatt SR drive motor generator provides up to 120 Newton meter torque assist during launch and yields an anticipation 10% improvement in fuel efficiency, fuel economy. This is typically hybrid powertrain for the dimension of Sri Lankan motor generator unit with the straight lamination diameter 284 mm, then straight active length 55 mm, rotor lamination bore 197, air gap 0.4 mm radial, and minimum battery voltage at full is 107 volt, low speed peak torque 120 Newton meter for 60 seconds, and low speed continuous torque 70 Newton meter, and base speed 450 kilowatt motoring 1200 rpm, and maximum design speed 6000 rpm. So, this Eddy Current Private Limited has developed this electric vehicle. As you can see the photograph of the car, a public limited company established in the year 1971. Eddy Limited company introduced first indigenously developed electric car The company is manufacturing electric car using Sri-Lankan motor for its propulsion system, and the company has manufacturing facility at Salkoda, Kerala, and Kobutor and Tamil Nadu. And these are the typically version of the Sri-Lankan motor for 29V series motor for high efficiency heating ventilation AC system from 1 HP to 3 HP or 5 HP or 15 HP. Then the of course 20 wind pinch Sri-Lankan motor drive motor for then the e-bike motors for mid drive unit and hub motor. So for aerospace application, as you can see, 20 kVA, 1500 propelled prototype starter generator rotor by Lucas Advanced Engineering Center. So aircraft industry is evolving towards an increased use of electrical auxiliary, particularly to replace hydraulic and mechanical power system. And aerospace industry demands not only very high performance but also extremes of reliability and fault tolerance. And SI drive technology designed and developed by Nidec SR Drive Limited can offer high fault tolerant design without recourse of redundant system as well as small size, high temperature operation, excellent servo performance. Although this application area is still in its infancy, and SR, you can call it SR Drive, has an experience in fuel pump system, starter generator, and secondary surface actuator, and is actually involved with new development in this area. So the application in automobile industry, features of SRM suitable in this field are high efficiency over wide speed range, and very compact, cost effective, robust, and reliable, fast tolerant, and sustainable. And this is of course used for vacuum cleaners. So here typically are the photograph and characteristic for of course blower. So MTech Lam Electro claim that Infin 8L SR drive motor blower represents the most powerful vacuum motor of its kind available, with the service life 3 to 5 times longer than the series of universal motor design. As you can see, photograph as well as characteristic like. So now Dyson had developed SR drive which runs at 100,000 RPM, and this is a square core motor with a built-in controller which manages energy consumption and provides the soft start and magnetic functions. And the first product to use new Dyson digital motor is a compact vacuum cleaner which have gone on sale in Japan this month with price tag of yen of 70,000 to 80,000. This 100,000 RPM motor spins more than 5 times faster a Formula 1 engine and has similar power to weight ratio. The control system pulses the motor and with energy 4 times per volume, requiring more than 400,000 signals decision and pulses every minute. And Dyson claims that the motor is the fastest ever developed for domestic appliances. That is up to 3 times faster than the conventional vacuum cleaner motor, built in smaller and weight about 1 kg compared to typical of 1.3 kg. Also generate 400 air watts as a measure of suck in vacuum cleaner. This is about a third more than conventional motor. This is of course typically for washing machine. As you can see, photograph of major domestic appliance manufacturer typically in the process. And the 3-phase Sri-Lankan motors is ideally suited for the wide range and high low speed torque required in front loading washing machine. The motor operated the drum through a belt drive and use a patent technique to operate a single position sensor. The electronics control board includes the custom ASIC specific application integrated circuit containing a specifically developed microprocessor and incorporating a number of novel features to extend washing machine control to new levels of performance. And it's also used like a food processor, cost effective die system for that at real value. As you can see photographs here of this motor food processor and centrifugal system. As you can see the photograph. So system is a major improvement over conventional high speed centrifugal, providing faster acceleration, faster deceleration, and higher G forces. So in fact, the top of the range of Avanti J301 is at a speed up to 30,000 RPM and generates a maximum force of 110,500 gram. The result is a versatile high throughput centrifugal which can produce 6 liters in less than it takes a conventional centrifugal to process 3 liters. At the heart of every Avanti J and JE system is a high torque SR drive motor and converter which produces twice the torque of a standard drive, making it possible to accelerate and brake the rotor in half the time of the conventional high speed systems. Now it's for bulk handling. As you can see, photograph for the bulk handling for different kind of, let's say, cement, you can call it the different kind of material. So match motor and controller designs assure system performs from the outset and allow the torque performance to be set within the range of driven equipment. And the simple SR drive rotor has significantly lower inertia than conventional wound rotor. Aging problem of refractory inertia in a high speed, high ratio geared application. So absence of any rotor conductor in the rotor minimizes rotor heat and permits unlimited starting duty even under full load conditions. So SR drive systems have an impressive track record in bulk handling applications, from their proven application in the mining industry to their use within the some of the latest development in the UK power industry. Now coming to application for conveyor belt, as you can typically see the photograph by SR Drive Limited system. So 5 SR Drive systems from 40 kilowatt to 160 kilowatt are employed on the blending plant, and 2 of these are drive on new installation and 3 are replacement for fixed speed induction motor. Like many applications, the installation benefits from the exceptionally broad operating envelope of SR drive systems and their ability to maintain very high levels of operating efficiency throughout the operating range. Another application in mining industry, flame-proof drive for potential explosive atmosphere, as you can see in the photograph. The diamond drive for underground operation, a flame-proof system which comprises reluctance motor and medium voltage controller. Both units are water-cooled and have been custom engineered to fully interface with the stringent requirement for electric equipment working in a potentially expansive atmosphere. So the system has Group 1 hazards area approval and ease of project construction to withstand the hazardous conditions of underground coal mining. So today, diamond drives are successfully used as a key materials handling application throughout the industry, and one such application is the underground at UK coals modeled by Colliery. Here, 3 150 kilowatt diamond drive systems are installed on a 2,300 meter long belt conveyor, and they provide the conveyor with the 3 operating speed for material movement, man riding and maintenance, and each with the torque limit control. And the conveyor has totally variable acceleration rate, and that give extremely smooth run up with the surge, thereby reducing the belt stretch and wear. So these are typically applications of 150 kilowatt drive motor at full load test, water cooled 35 kilowatt as termed for mining and other heavy duty applications with battery jamming. Another is AS handling, variable speed upgrade boost grab crane availability, as you can see in the photograph. So Nidec SR Drive manufacturer limited has supplied a 75 kilowatt variable speed reluctance motor drive system for one of the air grabbing cranes, replacing the aging slip ring induction motor on the winch drive system. And the brushless SR drive motor provides the high torque at slow winding speed required to raise and lower loads of up to 3.5 tons, and the precise torque control provided by the match SR drive motor and power converter allow the operator to raise, lower or hold the load using motor torque only. So this sustainability reduces the mechanical bearing and virtually eliminates the maintenance of braking system. And the superior thermal management of the SR drive limited motor allow the use of convection cooling without the need of for a fan, despite the motor confined position on the crane. Also, the motor ruggedness and simplicity have provided directs with the improved reliability in the area where access maintenance is difficult and expensive. Now coming to reluctance motor drive application to the compressor, the SR drive system are inherently soft starting with the smooth and control acceleration and deacceleration, reducing the stress on mechanical and electrical components. So compared to the conventional variable speed drive, the electronical control regulation schemes of LSR series simplify the system construction, resulting in a less to go wrong concept. And the L45SR and L75SR compressors have successfully provided users with energy and operational cost saving in excess of 25% over a conventional compressor. L120SR offers a greater output of between 2.75 meter cube per meter to 19.84 meter cube per meter, and the pressures from 5 bar to 13 bar with the even greater saving for large air users. Typical photograph of energy saving variable speed rotary screw air compressor. So another application is the pump, as you can see in the photograph. I mean, typically with the half the pump front, as you can show in the photograph. So the challenge of Weir was to bring the market new system that will afford higher levels of reliability, improved efficiency, and greater performance flexibility. And the VSR pumps are less than half the length of the equivalent standard pump package and provide significant improvement in performance and efficiency. In applications such as water injection and high pressure cleaning, their wide operating range and rapid run-up and shut-off capability provide major benefits, and precise valve speed control allow the operator to fine-tune the operating point of the pump to precisely match the process requirement. Now coming to application of air conditioning system, I mean, as you can see, environmentally friendly air conditioning system for passenger trains with a photograph of this. So in response to growing concern over the environment, impact of chemical refrigerant, air cycle system have been applied in the railway market to meet the today growing demand for environmentally friendly, reliable, and easy maintenance air conditioning equipment. In aircraft, air conditioning is powered by a compressed air blend from the engine. However, in a train, high efficiency SR drive motor drives a compressor to provide the source of air. So air is compressed in two stages, firstly by the SR drive motor compressor and then by the compressor side of the cold air unit. And the variable speed drive SR drive motor provides a soft start for the system and precisely matches the thermal load of the train carriage. At maximum cooling, the motor power is 40 kilowatt at a speed of 23,000 RPM, and the unit is operated at 670 volt DC power converter and weighs less than the conventional air conditioning system, allowing it to be entirely roof mounted. Now coming to application of sliding door operating system. So invisible performance meant developing a system that blended into the door architecture, that performed silently and that required next to no maintenance. And to achieve this required a more compact mechanism incorporating the highest possible precision, safety, and dependability. The result is an operating system capable of opening all types of door in opening from 900 mm up to 3 meters and with 7 program opening alternative. At the heart of system is an innovative direct drive unit powered by a custom designed reluctance motor system, and the SR drive motor eliminates the need for a gearbox, which is usually the component that creates noise in the door system. This, together with the drive inherently efficiency and reliability, means quieter operation and lower service cost. These are the slider door operating system. You can just see with the sliding door operating system with the individual reluctance motor and innovative sliding door operating system with direct drive unit powered by a custom design SR drive. So reluctance motor drives provide a quieter operation, lower cost. Now coming to typically motion control application, deliver fast response and high accuracy in compact packages. Here you can see pick on a camera repair wearing machine using SR drive in both the mains and it, and typically 2-axis quadrant SR control system with the Simpson Morgan Hall company. So another is wheel loader. You can see the photograph of delivering responsive torque dependable traction system. So Liniton invented the electric drive wheel loader more than 40 years ago and has been refining the concept ever since. So today its range of loaders represents the industry standard and includes the largest front end loader in the world. So L1350 standard stands 6 meter height from the ground to cab roof and more than 16 meter long. It weighs over 180 tons and its 21 meter square rock bucket handles a 38-ton payload. And the loader is powered by 4 B40 type SR drive motors, one for each traction wheel, each providing torque up to wheel via 141 to 1 planetary gearbox, and each B40 motor is rated at 300 kilowatt, yet its physical size is comparable to that of conventional 150 kilowatt motor. So the wide torque bandwidth of this Liniton SR drive system delivers exceptionally high tractive effort and maximizes the benefit on board control scheme that minimize wheel slip and tire wear. And all 4 SR drive system operate as a gear generator as well as motors, allowing the vehicle to be brake electrically relative to the original brushed DC motor, that SR driving system replaces the absence of brushes and commutator in SR drive machines, provides a major increase in the service and inspection interval, about 500 hours to the 2000 hours for bearing replacement. Now coming to general traction systems. So Blackpool is one of the few UK towns that retain a Stamps streetcar system. So Ford is sanitary in 1985. Visibility study were set to evaluate the new technology which could replace the traditional DC motor and resistance controller. So Nidec SR Drive Limited was invited to give a set of 4 SR Drive traction system for one of the small motors of new vehicle based on coach chassis, which would be used to as a demonstrator vehicle. The tram zone had 4 drive, each driving 1 XL, and based on totally enclosed SR drive motor, which were supplied from the 600-volt DC catenary. The motor were mounted on the bogies, and the GTO-based controller were mounted in a cubicle in the passenger compartment. And this is typically the successful feasibility study of car traction drive. So drive had peak rating of 300 Newton meter, 30 kilowatt, and 3000 RPM. And after initial commissioning, the trams was put into full revenue earning passenger service and performed very successfully, covering over 15,000 miles before the study ended. It was particularly favored by the drivers who appreciated the smoothness of the control and wide speed range of the drive. So some of the other variable speed drive manufacturers are typically here: 24 volt 6000 prototype SR showing the elimination, and other courtesy of advanced courtesy UK Center and 4 phase. And then so these are the series of Allen West variable speed drive 7.5 to 22 kilowatt reluctance motor drive. So selection of reluctance motor rating from 100 watt at 5000 RPM to 100 kilowatt at 1500 RPM. Courtesy reluctance motor drive limited UK. So now coming to primary features of reluctance motor. Reluctance motors is a brushless AC motor. The phase winding of its stator only, and rotor contains no winding conductors on permanent. The usage electronics commutation rather than mechanical brushes and commutator or silvering, and rather simple low cost machine. Operation over a wide temperature range without performance degradation due to absence of magnets, and highly efficient motor and inverter. Very high speed capability, high starting torque capability. Unipolar phase excitation require a minimum of 1 switch per phase. Very high torque to inertia ratio for good acceleration and reversing characteristic. Useful open circuit and short circuit characteristic. Very long life and reliable machine with inverter life comparable to other inverters, and operating characteristic can easily be programmed. Disadvantage: it cannot operate from the AC line power without some sort of converter or controller, and very high audible noise proportional to speed. Relatively high torque ripple. Speed torque characteristic is highly nonlinear. Require very small mechanical air gap to achieve high torque volume per weight, and requires soft position feedback data for phase commutation and most complex wiring connection compared to any other motor. Now comparing the reluctance motor with synchronous reluctance motor. So here in reluctance motor, both stator and rotor have a silent pole. In synchronous reluctance, stator have a smooth bore except the slotting. And in case of synchronous motor, stator winding comprise a set of coils, each of which bound on the one pole. In case of synchronous reluctance, stator has polyphase winding and with approximately sinusoidal distributed coil. In case of reluctance, excitation is in sequence of current pulses applied to each phase winding. In case of synchronous excitation, set by polyphase balanced sinusoidal waveform current. In case of reluctance motor, phase flux linkage should have a triangular or sawtooth waveform, but not vary with current. Here the synchronous reluctance, the phase self-inductance will vary sinusoidally with the rotor position, but should not vary with the current. Now comparison of reluctance motor with variable speed stepper motor. The reluctance motor normally operated with the soft position feedback to synchronize the commutation of the phases with the precise rotor position, and normally designed for efficient conversion of power up to at around 300 kilowatt. And variable reluctance stepper motor normally run in open loop, that is without soft position feedback, and normally designed to maintain a high step integrity rather than the achieve efficient power conversion. So now differences between reluctance motor machines and classical machines. The classical theory of torque control in electric drives is based on the DC machine, in which the torque is proportional to flux multiplied current. The flux and current are controlled independently, and the orientation of the flux and ampere conductor distribution both in space and time is fixed by the commutator. And in AC field oriented control, mathematical transformation are used. In effect, to achieve independent control of flux and current, and the commutator is replaced by the short position sensor. In classical DC and AC machine, the flux is maintained constant while current is varied in response to the torque demand. So in silicon motor, unfortunately, there is no equivalent torque kilometer control. The torque is produced in pulses, and the flux is in each phase must be usually be built up from 0 to return to each phase to 0 in each stroke. The orthogonality of the flux and current is very difficult to contemplate because the machine is singly excited, and therefore armature current and field current are indistinguishable from the actual phase current. So SRM does not have sinusoidal displacement or a smooth air gap, therefore there is virtually no hope of field under control. To achieve the continuous control of instant torque, the current waveform must be modeled according to complex mathematical model of the machine. Now coming to construction of reluctance motor, as you can just see here, you have a typically 3-phase with the typically 12 poles on stator and typically 8 poles on the rotor. So it's a 12 by 8, so it can be 3-phase. Coming to the reluctance motor consists of stator, rotor, and the phase winding. For the position determination, position sensors are used. So depending upon the rotor position, the phases are excited are energized for the motoring or generating operation. Unlike the conventional reluctance motor requires a specific converter, and the selection of the converter depends on the number of phases, cost, and desired control accuracy. So you can see how the stator look like here. The typically concentrated winding. The stator made of silicon steel stamping with inward projected poles, and the number of poles on the stator can either be even number or an odd number. So most of the motors available have even number of stator poles like 6 or 8, and all these poles carry field coils. The field coils of opposite poles are connected in series such that their MF are additive, and they are called phase windings. An individual coil or a group of coils constitute a phase winding, and each of the phase windings are connected to the terminal of the motor, and these terminals are suitably connected to output terminal of a power semiconductor switching circuit whose input is the DC supply. Now coming to the rotor, as you can see in the photograph of two different motors, the rotor is also made of silicon steel stamping with outward projected pole, and number of poles of the rotor is different from the stator poles, number of poles on the stator. In most of the available motors, the number of poles on the rotor is 4 or 6, depending upon the number of stator poles, 6 or 6. So here coming to typically the cross section area of the reluctance motor machine of 6 by 4 interior rotor and 8 by 6 exterior rotor like. So now rotor shaft carries the position sensing unit. Rotor shaft carry the position sensor. The turning on and turning off of position of various devices in the power semiconductor circuitry are influenced by the signal obtained from the rotor position sensor. And motor, the rotor position is determined by using optical sensor, Hall sensor, or encoder. And this is a sensing circuit photograph, as you can see in the typically position rotor angle sensor using a photocoupler, and other sensing unit with the typically Hall effect sensors. Then other typically using the position or rotor angle sensor using encoders like. So coming to the converter, or power converter for exciting the machine. So mutual coupling between the phases is negligible in a reluctance motor, and this gives the complete independence to each winding for control and torque generation. And all the converter topology except the two-stage power converter, assume a DC voltage source is available for their input. So maximum power converter topology with Q plus 1, 1.5 Q and 2Q switch topology, where Q is the number of the machine phases. And here the classification of converter configuration for Q phase machine with two-stage power converter, two switch power converter, two switch asymmetrical and variation asymmetrical with the higher than 2 switch, then 1.5 switch per phase, 1.5 Q switch, then Q plus 1 switch equal sharing C dump with prevailing shared switch, minimum switch with variable DC link with the buck and buck boost and resonant, and single switch per phase, R dump bifiller split supply Q switches, 2Q diode, independent phase current control and dependent phase control. And this is typically a symmetric converter for SRM with prevailing regeneration capability for can be extended for any number of phases. So we have a 2 switch and 2 diode. When switch on, the phase winding is excited. When one switch is off, then we have a prevailing mode. Any one of the switch off, then prevailing mode. And when both the switches off, the negative voltage applied typically across the winding because of the diode conduction, and it reduces the current to really come to the 0 when we want to de-energize the phase like. This is another converter, R dump converter for SR drive with prevailing regeneration capability. typically, I mean, here you have a one switch per phase, and you can see when transistor is on, your phase current conducts, and when transistor is off, of course, the diode conduct to charge the capacitors, and of course, the resistance will go to the DC link. Then you have a typically bipolar for the SRM with freewheeling and regenerative capability. So when you switch on, the current conducts, and when you switch off, of course, freewheeling that conduct to recover the energy back of this. You can call it the bipolar winding. Then the converter with midpoint on split type of DC converter for freewheeling, and this is used for even number of the phases, and we use the midpoint for, of course, so you can have a half the voltage are applied across the phase, and when typically when switch is closed, and then when switch is off, then freewheeling action, you get a negative voltage because of the diode conduction. Then you have a converter modified single switch per phase converter for the silicon freewheeling and regenerative capability. So you can just see when you are really exciting, I mean, you are switching on, then it phase conduct, and when you switch off, obviously the diode conduct and recover the energy back. Then this is a converter with single switch and 2 diodes per phase for exciting the different phases. Typically, I mean, with the energy coming to the typically the capacitor provide the path for. Then you can call it C dump with energy recovery circuit. So it comes the energy on capacitor when you switch off the devices, and then if capacitor voltage is beyond a level, then we switch on TR transistor and or MOSFET and go to back to the source via inductor and DR. Now coming to operating principle of reluctance motor. The operating principle here is the torque produced in the reluctance motor is explained using the element principle of electromechanical energy conversion in a solenoid, and the solenoid end turns, and when it is excited with the current I, the coil sets up a flux phi. So increasing the excitation current makes the armature move towards the yoke which is fixed. So the electrical input energy is written as W equal to integration of EI DIT or integration I dt d phi dn phi upon dt, or Ni d phi, or integration F d phi. So where E is the induced EMF and F is the MF. This input electrical energy W is equal to the sum of energy stored in the coil WF and the energy converted into mechanical work WF. So W equal to WF plus dm Wm. For incremental change, it can be written delta E equal to delta We plus delta M, and you can just see how the really is the moment by exciting. So you can say electrical input energy written as delta We phi 1 to phi 2 F1 d phi, or F1 phi 2 minus phi 1, area B C D E F in the diagram, and delta F is your delta F1 X equal to X2 and minus delta F X equal to X1, that is area OCDO minus area OBEO in the two diagram. In the diagram with the different notation, the incremental mechanical energy derivative delta M equal to W minus delta F, that is area OBCO. So in case of rotating machine, the incremental mechanical energy is in terms of electromagnetic force and torque, and change in the position is given as delta Wm equal to T into delta theta, where T is the electromagnetic torque and delta theta is the incremental rotor angle. Hence the electromagnetic torque is given as T equal to delta Wm upon delta theta. Now coming for the case of constant excitation, when the MF is constant, the incremental mechanical work done is equal to the rate change of co-energy, which is nothing but the complement of field energy. Hence the incremental mechanical work done is written as delta Wm equal to delta Wf dash, where Ws dash is nothing but integration phi df or integration of phi d ni, or integration n phi di, or integration lambda as a function of theta I into di, or for linear magnetic circuit integration L theta I di, which also called co-energy. Like hence the air gap torque is T equal to delta Wm upon delta theta, or delta Wf dash or delta theta, or equal to delta F dash as a function of I theta divided by delta theta at I equal to constant. So if the inductance is linearly varying with the rotor position for a given current, then the torque can be derived as T equal to dl L theta I upon d theta I square, where dl upon d theta equal to L theta 2 minus I theta 2 L function is theta 2 I minus L theta 1 I divided by theta 2 minus theta 1, where I is constant. Now coming to equivalent circuit of reluctance motor. The equivalent circuit here you can just clearly see with the battery connected and RL and the back EMF. So due to Salient structure of Sri-Lankan motor, the air gap between the rotor and stator pole changes based on the relative position on the rotor and stator. For this reason, the phase inductance in SRM is dependent on the rotor position. Therefore, the flux linkage expression of SRM is as lambda equal to L theta I. So the voltage at the phase terminal is given V equal to IR L theta di upon dt plus I dl upon d theta dl theta upon dt, that is equal to IR plus L di upon dt plus I dl upon d theta or d theta upon dt, where omega is d theta upon dt. Then V equal to IR plus L theta di upon dt plus I dl upon d theta into omega. So now coming to power and torque in reluctance mode, the power conversion process in reluctance mode can be derived as V equal to I square R, that is losses IL di upon dt plus I square dl upon d theta into omega, where IL theta di upon dt is equal to d upon dt bracket half Li square or minus half I square dl upon d theta and d theta upon dt, or IL di upon dt equal to d upon dt bracket half L I square, that is minus half I square dl upon dt into omega. So power equation of SRM is calculated now. I equal to I square d upon dt half L di L I square plus half I square dl upon dt omega. So input power goes to copper loss, then magnetic stored energy, then mechanical power, and from the last term we can get the mechanical power equal to T omega, and from which we can get the T equal to half I square dl upon d theta for linear magnetic circuit. Now coming to a non-linear and non-linear modeling of the and characteristic of reluctance motor. So simulated model here you can just see, we give the stator voltage for winding and we integrate, we get the flux linkage, we have a magnetization characteristic from which we get the typically the current, and from current and position, rotor position, we get typically the torque, and of course torque goes to mechanical section, output of which torque, speed and position. Of course here we use the typically for theta pump as a feedback for this model. Now coming to flux linkage measurement, two methods of flux linkage calculation are DC excitation and AC excitation. The magnetic flux linkage is obtained from by the equation psi theta psi s as a function of t 0 integration 0 to t vs minus rs is dt, where is vs rs is represent the magnetic flux linkage, stator voltage, stator resistance and current across the winding respectively. And coming to a case study opening the characteristic of 3-phase 12/8 SRM, where the number of stator and rotor poles are 12/8, power 1.2 kilowatt, rated current 28 ampere, speed 3300 rpm, voltage 488 volt, rated torque 3.47 Newton meter, underlying inductance 0.5 millihenry, underlying inductance 3 millihenry. So now this is the typical stator winding resistance that we can use a battery of variable with the resistance, sectional resistance, and then voltmeter ammeter, and with the resistance inductance. Resistance measured by using voltmeter method, and stator winding resistance measured is 0.143 ohm. Now coming to reluctance motor for rotor locking arrangement for getting psi characteristic, as you can see couple of the motor photograph with the locking arrangement. I mean one of motor coupled here with locking arrangement from different sides. So coming to flux linkage characteristic, you have a battery with the switch, solid state switch. Normally we use the IGBT here, and with the 1 Hertz pulse signal from DSP, and then we have a typically freewheeling diode across the winding, and then we have a current and voltage measurement for the CRO which record the data. So voltage and current reading were taken with the help of digital storage CRO, and data of 1000 sample were available, from which 200 samples were taken, and this process was repeated for half of the rotor pole pitch to get the complete characteristic from unaligned to aligned position. And this is, you can see, flux linkage measurement, how the voltage and current waveform at unaligned position and voltage current at the aligned position. So from this we get a flux linkage characteristic, as you can see here at different rotor position from unaligned to aligned position, and we get how the flux and at different theta. This was for typically with the current 3-dimensional characteristic of flux linkage. Then you can have a co-energy in joules, also the characteristic with the current, and then you can have a co-energy with the function of current and rotor position, a different rotor position in 3D. And then from this you can calculate the torque and rotor position characteristic as it is shown, and then of course the 3-dimensional as a function of, you can call it, position and the current. So now coming to typically the SRM model configuration. So static torque production in linear analysis of synchronous motor. As you can see in the diagram, we have a characteristic lambda versus I, and typically at a particular theta where the co-energy and energy, co-energy WC and WF is the stored energy, field energy called WF minus I d lambda, and co-energy is the WC, that is integration lambda di. So the linear analysis assumes that the inductance is unaffected by the current, that is there is no magnetic saturation, and for simplicity the fringing flux is also ignored. The instantaneous torque T equal to d omega c upon d theta at lambda constant, or T equal to minus d WF d upon d theta at lambda constant. So the flux linkage is lambda equal to Li. So field energy and co-energy become equal for linear case. So WF equal to WC half Li equal to half Li square. Therefore the torque developed by both the way it equal to half I square dl upon d theta, where the dl upon theta is the slope of the inductance variation. You can just see if slope is positive, you will get a positive torque as a motoring, and if you really have a slope of dl upon theta negative, then you will get the negative torque. And of course the torque is proportional to current to square, so it does not depend on the direction of the current, whether current is positive or negative in the motor. So you can just see here is coming to static torque production in nonlinear analysis. As you can see here, in with the saturation you have a flux versus flux linkage characteristic, where the co-energy and stored energy are shown WC and WF. In nonlinear analysis, the stored energy WF and co-energy variation is assumed nonlinear. So value of flux linkage calculated as lambda equal to at the integration V minus R at dt. From the voltage equation, V equal to Ri plus dl lambda upon dt, assuming that the flux linkage is a function of current and rotor position. So lambda is a function of I and theta. So now coming to following expression, I use d lambda upon dt equal to V minus Ri, and the speed derivative j d omega upon dt equal to E minus TL, and t theta upon dt equal to omega. So stored energy WF is defined WF equal to integration I d lambda, and lambda is a function of lambda is a function of I and theta. So typically you can see the energy exchange, of course, for linear circuit which are shaded is responsible, we call it the typically energy converted to mechanical work as in a one stroke angle, and for non-linear characteristic also you can see how much is the energy, I mean typically is get converted into one stroke angle represented by psi characteristic of the motor, I mean unsaturated and saturated region. So of course with the saturation you can clearly see the machine, or this machine can produce the more output. So now you can just see how the phase inductance profile varies here, I mean for unaligned to mid aligned and completely aligned, and how it is the characteristic shown completely fully aligned, unaligned position, and aligning position. So you can just see how the phase inductance varies, flux linkage varies with the position for, I mean how you really typically excite, I mean with the constant current, so how the torque is produced with the unaligned. You don't have a torque produced in aligned position as well as aligned position, you get the torque produced positive or negative under aligning condition. And here is the, of course, the inductance profile corresponding to effect of saturation on the inductance profile line. And this is the torque profile for motoring and generating region when you really excite with the constant current for one side electrical side. Now coming to simulation model of SRM. A simulation model for the experimental register SRM is achieved using a MATLAB Simulink environment. The model uses the data obtained from measurement to avoid the inaccuracy inherent to the analytical model. The characteristic of current versus rotor position, flux linkage versus rotor position and current are stored in lookup table and are introduced in the model of SRM. So the model can be further used in the optimization of control and or design. Although these models are very close to the real behavior of the machine, the mutual coupling between phases as having a small influence on the machine operation is not taken into account. So you can say here that for the simulation model, as this is shown here, simulation of one phase with the voltage as the input and the position coming out, and we get the current and then the developed torque from these characteristics. So these characteristics I as a typically function of lambda theta and torque as a function I theta are used here to get the typically current as well as the torque. So modeling and simulation of one phase of SRM shown in figure. The inputs are rotor position and phase voltage, and the output are phase current and torque. So the SRM cannot run directly from AC or DC source. It requires continuous commutation from one phase to another. So the motor itself and its converter are considered in one unit. So for system simulation, the converter and position sensing unit need also to be modeled. The most common converter for SRM is the asymmetric bridge converter. Now coming to phase excitation sequence of SRM. With respect to the given phase, there are two important rotor positions to identify electrical cycle unallying and aligning position. So phase 1 is at the unallying position, which is designated as 0 degree electrical by the convention. Therefore, 180 degree electrical is the aligning position. So in motoring mode, each phase will be excited sequentially in the positive slope of flux linkage profile or rising inductance zone. And for a 12 by 8 SRM, the phase excitation order of phase 1, 2, 3, 1, 3, 2 for counterclockwise operation. And this is the typically phase excitation sequence for ideal flux pattern. Then long path for during the single phase excitation and residual flux during phase commutation. So now coming to here with the inductance, you can see clearly how the flux linkage, ideal flux linkage, which represents current 1, and then the if you have a current ideal current with all the three phases, then how it is the really the phase current commutation can also take place with the practical current. So ideal phase excitation sequence for three phase, ideal flux linkage excitation for phase 3 and phase 2, and then phase current. And then of course the simulation result for low speed and high speed. So for low speed we have a chopping mode. You can see the voltage in the chopping mode we are exciting, and there is a ripple current the top. It takes some time to build up the current and reduces, and then how the flux also produces. Flux is also not constant as changing. And when it go to high current, high speed, then of course we don't go chopping mode. It's only the single pulse mode. For rising current we have a positive voltage, then negative voltage for quenching the current, and then the flux linkage comes as a typically as a triangular way because of all the time voltage applied and then positive and negative voltage applied during rising current and falling current. And here you can just see how the DC current control of reluctance motor, phase current, phase torque, and torque, net torque of the motor. Like so, you have a different color for different three phases excitation current, then the torque produced by them, and then the net torque with the certainly some ripple in the torque. Like so, ideal phase inductances of three phase SRM. So the symmetry of magnetic circuit leads to almost zero mutual flux linkage in the SRM phases even under saturated condition. This meant that the SRM will work with N-1 phases with no induced voltage or current appear in the short circuited phase. You can see clearly non-saturated and typically motoring and generating, where you have to really excite for with the symbols. Rising inductance we excite for the motoring, and falling inductance we excite for the generating. That's current out. So this is typically the phase inductance profile of SRM rising and falling with the current, motoring in the rising and falling. And then when we go to high speed, of course, for motoring, and you can call it how the current are there for high speed operation. And then the typically the phase energization with the how the current is there with the phase excite energizing with the typically with the dual angle, and we have to advance the angle to build up the current at the aligning position for the maximum value also. Then of course with the three phases how the current in different speed in the low speed chopping. Ideally we want a current of Cauchy square waveform, but practically it is a chopping. It takes some time to build up the current and fall the current, and as you go high speed it's very difficult to maintain the current because of back EMF. You can see the lower at higher speed and how the current typically with the inductance variation and voltage applied to the motor winding. Then of course the torque is the characteristic of reluctance motor, constant torque region for the lower speed than the constant power characteristic, and then we have a variable power speed. When we go high speed, it is very difficult to maintain the current even to the relay current. So these characteristics, of course, can be suited for different range. Up to WB or WC, or different bit WC can be tailored for different type of application. These characteristics, like so that it suits whether it is for tracking application or it is for universal motor application. So which application you are going to select, accordingly you can tailor the characteristic and you can modify the design of the motor to really have a different range to extend for wider speed range. Now coming to theoretical problems. So question 1, what is the fundamental principle of operation in a reluctance motor? SRM reluctance motors operate on the principle of variable reluctance. Torque is produced by aligning the rotor poles with the stator pole, and the reluctance of the magnetic circuit is varied by changing the alignment, leading to the generation of the torque. The question 2 is what is the key advantage of reluctance motor over the permanent motor? So one key advantage is the lower cost, as a reluctance motor typically do not require a earth magnet, making them more cost effective, especially in application where the cost is a critical factor. Question 3, how are the phases defined in the context of an SRM? Phases in SRM refer to the windings on the stator. These windings are energized in a sequence to create the rotating magnetic field which interact with the rotor to produce the motion. What is the primary factor influence the torque production in SRM? The primary factor influencing the torque production in SRM is the phase current. As the current in the stator winding changes, it affects the magnetic field and consequently the torque generated by the motor. Question 5. Which one is the following is a common application for reluctance motor? The electric trains are the common application for reluctance motor. Characteristic of reluctance motor such as robustness, high torque at low speed make them suitable for traction in electric train system. What are the constant control techniques for SRM? The control technique used in SRM: current chopping control, advanced angle control, and single pulse control. Question 7. What are the advantages of reluctance motor? The advantage of reluctance construction is simple and robust. Rotor carriage no winding, no slip ring, no brushes, less maintenance. There is no palming net. Ventilating system is simple and losses take place mostly in the stator. Power semiconductor switching circuit is simpler. No should throw fault likely to happen in power short circuit, and developed torque does not depend upon the polarity of current in the phase line. Now question 8. Explain the aligned position. The aligned position by rotor poles are at 0 degree or 14 degree. Maximum inductance, torque, and magnetic circuit like to saturate on line when the rotor poles are at 90 degree. Minimum inductance, 0 torque, and magnetic circuit is not saturate. Now coming to numerical problems. The question 1. The 4-phase 1.2 kilowatt 3300 rpm electric motor with a stator 8 stator and 6 rotor poles have a stator pole are 20 degree and rotor pole 24 degree. Aligning inductance 3 millihenry and aligning inductance 0.5 millihenry. Resistance of winding 0.6 ohm. The saturation can be neglected. The SRM is fed from a battery of 48 volt terminal voltage. The motor is used in an industry as a pallet truck. Calculate the peak battery current, peak, and RMS winding current to obtain the instance torque 4 times than the rated torque at starting when 2 phases are excited simultaneously. So coming to the solution, rated torque P upon omega s, so that's putting 1200 by speed, that's 3.47 Newton meter, and 2 phases are excited. The torque by each phase is 4 into rated torque by, so it's comes 6.494 Newton meter. D theta equal to beta s 20 degree, 0 equal to 0.384 radian, and torque from half I square dl upon d theta. So instantaneous starting rated current is I under root 2 d theta upon dl, and putting value it comes 46.17 ampere. And then the RMS current I RMS equal to PR upon 2 pi 0 to BR I square d theta under root of that, putting value it comes 27.96 ampere. So since the two phase are excited, so peak battery current is ID equal to peak, that is 2 into 27.96 into that 79 ampere. Now question 2. In the 4-phase reluctance motor with 8 stator pole, 6 rotor pole width of stator and rotor same 20 degree, the aligning inductance 110 million and aligning 15 millihenry. The current of 20 ampere is in phase winding are applied when the inductance are increasing. Calculate the average torque produced by one phase and the inductance are increasing with constant current excitation. So here for solution, DL equal to LA minus LU, that is 115 minus 15. So that's a 95 millihenry, and d theta equal to b dash, that 20 degree, do 0.349 radian, I equal to 20. So from torque T equal to half I square d upon theta, it comes 54.43 Newton meter. Now coming to question 3, a reluctance motor with the 6 stator and 4 rotor poles has a stator pole arc of 30 degree, rotor arc 30 degree, aligning inductance 50.7 millihenry and aligning inductance 5.5 millihenry. Situation can be like calculate the position at which the minimum value of the inductance occurs from the point where both the poles are lying, neglecting the thinking. So from the figure quad here, so minus beta s equal to minus 30, so beta s plus beta r minus beta s equal to br, that is 30 degree. Now question for a 3 HP 1500 to 200 volt 8 by 6 SRM having a stator and rotor pole arc of 20 degree and 21 degree respectively. The aligning and aligning inductance of the machine are 110 and 10 millihenry. Find the ratio rate change of the inductance. So in the region when the start to align is a DL equal to LA minus LU, so 110, that's minus 10, that is 100 millihenry. Theta equal to beta is 20 degree, that is 0.35. So DL upon d theta putting value it comes 0.286 Henry per radian. Question 5, a 4-phase 4 kilowatt 1500 reluctance motor with 8 stator and 6 rotor pole has a stator pole of 25 degree, rotor pole arc 22.5. The aligning inductance is 110, aligning inductance 11 millihenry. Saturation can be like calculate the winding current to obtain torque 8 times the rated torque of 80% of the rated speed when the one phase can be excited. Again, rated torque is TR equal to PA upon W, that 25.46 Newton meter. Torque required 8 times TR 203.71, and d theta is beta equal to 22.5, that is 0.92, and dl equal to LA minus LU, that's a 99 millihenry. So from t equal to half Li square, so putting the value of current comes 40.16 ampere. So in question 6, in three-phase reluctance motor has a 6 hysteresis pole. The hysteresis poles are sequentially excited by the total times of 10 milliseconds for one. Find the angular velocity of the rotor in position. So since the rotor pole pitch is 6 by 4, that's 90 degree. In one cycle, rotor pole rotates 90. So one revolution of rotor have 4 cycles. So time taken for rotation for one revolution 4 into 10, that is 0.04 second, and at in 40 milliseconds there is no one revolution. So in 1 minute the number of revolutions 65.0, that is 1500. So angular speed is 1500 rpm. Question 7, a 4-pole 500 rpm reluctance motor with 8 starter and 6 rotor pole has a starter pole arc 30 degree, rotor power of this allowing inductance 20 milli, and the allowing inductance 2 point resistance is 0.25 ohm. Saturation can be electric as a 8 device converter is fed from the battery of 48 volt used to supply 4-phase starter winding of the motor. The motor is used in an industry as a pellet truck. Calculate the peak current and the rated torque at 50% of rated speed with the 2-phase axle simultaneously. So rated torque is P upon omega, that's 28.65, when the 2 phases are conducting. So torque supplied by each phase is half of that, that is 4.5. Theta is beta equal to 2.5, 0.392, and DL equal to that is 22.5, and from the torque expression of T equal to half I square del upon P current I comes under 2 d theta upon this comes 22.33 ampere. Now question 8, find the stroke angle for 6 by 4 and 10 by 8 and 3 by 8. So stroke angle is theta 2 pi upon NR, n phase NR. So for 3 phase theta comes, putting a value 30 degree, and 5 n phase equal to 5, it comes 90 degree. For when 3 phase it comes like 15 degree. Now question 9, in the 3-phase reluctance motor with 6 starter and 4 rotor poles, width of starter and rotor is at same as 40 degree, then the allowing inductor 0.7 millihenry and allowing 1.5 millihenry. The peak to current of 16 ampere in winding is fed from the inductance and increasing. Calculate the torque developed by the motor. If developed torque is required double of this value, calculate the required peak and RMS current in the winding. Situation like that. So considering the theta 1 equal to half 2 pi upon PR minus beta plus beta plus beta r, so minimum inductance occurs at theta 1 equal to 0.08 and theta equal to this theta 1 plus the theta, so it comes 0.78, and assuming no saturation, so its slope is LA minus LU upon theta 2 minus theta 1, it comes like 0.01606 millihenry per radian. So the T rate half square d upon theta, putting value it comes 2.0538 Newton meter. Since the required torque is double of the rated torque, so therefore the peak current of the motor winding IP equal to 2 theta d upon d theta, that comes 22.631 ampere. RMS current of winding is PR1 to Y, theta 1 theta 2 I peak square d theta, putting value it comes 15.08 ampere. Now coming to question 10, what is the step angle of 3-phase reluctance motor having a 12 starter pole rated rotor? What is the commutation frequency in each phase at a speed of 6000 r? Step angle is 2 pi upon Q into PR radian. So Q is number of phase, PR is the number of poles. So theta, putting a value, it comes 15 degree. Commutation frequency is 1 phase F1 equal to NR PR, it comes 800 Hz. Now coming to question 11, what is the step angle of 5-phase reluctance motor having a 10 poles on step pole 100? What is the commutation frequency of each phase at 6000 rpm? Step angle theta upon equal to pi upon Q PR. Q the number of phase, PR is the number of rotor poles, so theta comes as 18 degree, and the commutation frequency is NPR, it comes 400 Hz. Now question 12 is reluctance motor with 6 starter pole 4 rotor poles has a pole arc 300 and rotor 30 degree and rotor pole arc for 32 degree, allowing position 10.7 millihenry and allowing inductor 1.5. Saturation current neglect the instantaneous torque when the rotor is 30 degree before the allowing position and phase current 7 ampere, neglect that. So T equal to half I square d upon theta, so calculating theta 1 half 2 pi upon PR minus beta plus beta r. So minimum inductance theta 1 is 0.244 radian and minimum inductance occur at allowing position. So theta 2 is your 0.7678 radian. No saturation, no filling, so slope is LA minus LU theta 2 minus theta n, that equal to 0.0175, and T rated is you calculate 0.43 Newton. Now coming to question 13, a 4-phase 4-pole 1500 reluctance motor, 8-pole 6-pole rotor has a starter pole arc 30 degree, rotor power arc 22.5, length Newton 110, inductance 11, the resistance is 1 ohm, SRM is fed from 280 used for To apply 4-phase stator winding of the motor, motor is on industrial practice to calculate the average torque, peak torque, RMS current to obtain the instantaneous torque 8 times than the rated and starting and 2-phase axle. So rated torque is PS over omega 25.46 when the 2-phase axle conduct torque supplied by 8 times rated by 2, that is 101.86. dt type beta r 21, that's a 0 1, and torque from equation T equal to half dt का तो I under root 2 theta d upon dt, that comes 28.42 ampere, and RMS current is your RMS P upon 2 r 0 to beta r I square d theta, it comes 17.4 ampere. This two phase excited, so average battery current is ID equal to, bring value here to 22.31 ampere. Question 14, a reluctance motor with a 12 pole stator and 8 pole rotor has a stator pole arc 10 degree and rotor bar 16 degree, aligning inductance 80.5 millihenry and aligning 12.5 millihenry. Saturated neglected, calculate the instant torque when rotor is 30 degree before the line position, phase current 15. Rotor pole pitch is 3 by NR, that is 45 degree. Inductance profile of a particular field will have increasing portion of 10 degree. So beta equal to 10 degree, beta r equals 16. So 30 degree before line, the inductance will have the negative slope. And this is the inductance variation as you can see from there. Coming to question 15, a 3-phase reluctance motor with 6 pole stator and 4 pole rotor, 4 pole width of stator rotor 40 degree, allowing inductance point, allowing 1.5 and current 10 ampere. Now inductance in P, calculate the average torque by the motor flat for 30 degree, 20 degree, 20 degree, 30 degree and 60 degree. So you can see different currents and different conductions. So you can just calculate the torque produced for any phase when inductance is increasing. T equal to half I square dl upon dt, so it comes 0.6589 Newton meter. The rotor pole pitch of 90 degree when the conduction is 20 degree, average torque produced by the motor, that comes typically 16 to T upon 90, so that comes 0.4926 Newton meter. And when the conduction 30 degree, the average torque produced is 90 upon 90 into theta, that is 0.659, and when conduction 40 degree, comes 30 into 2T plus 60 into T by 90, that comes, putting value, it comes 0.8785 Newton meter. These are the references or textbook to prepare this material, so you can just refer these, and thank you.